Tonight, we're going to explore something so familiar that most people never stop to question it. Light. It fills every room you've ever stood in. It lets you read these words. It travels from distant stars into your eyes every single night. But here's the question almost nobody asks. Why does light move at the speed it does? And not faster or slower, but at 299,792 kilometers per second, a number so precise that physicists use it to define the meter itself. Where did that number come from, and what is it about the universe that makes the speed of light exactly what it is, and not something else entirely? By the end of tonight, you're going to understand where light gets its speed from, why nothing in the universe can catch up to it, and why the answer isn't really about light at all. It's about the structure of reality itself. Before we begin, if you enjoy these topics as much as we do, make sure to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Pull back from light for a moment and think about electricity. You flip a light switch, and the bulb turns on almost instantly. That feels like the electricity is moving fast, but that's not quite what's happening. The electrons in the wire, the actual charged particles, barely move. They drift through the copper at a speed of about 1 millimeter per second, slower than a snail. What travels fast is the electromagnetic disturbance, the wave of electrical pushing and pulling that propagates through the wire and carries energy from the source to the bulb. That wave moves at a large fraction of the speed of light. Now hold that image. A wave moving through a medium. Because understanding the speed of light requires you to think in waves first, and to think carefully about what those waves are moving through. In the middle of the 19th century, a Scottish physicist named James Clerk Maxwell sat down to unify two things that almost everyone thought were completely separate phenomena: electricity and magnetism. On the surface, they seemed unrelated. Electricity was about charges and currents and sparks. Magnetism was about compass needles and iron filings and lodestones. And yet, experiments across Europe kept showing they were deeply connected. Move a wire through a magnetic field and you get a current flowing through that wire. Run a current through a wire and you create a magnetic field curling around it. The Danish physicist Hans Christian Ørsted had noticed this connection in 1820, when a compass needle deflected as he passed current through a nearby wire, right in front of a lecture hall full of students. That accident changed physics. The French physicist André-Marie Ampère had described how currents produce magnetic fields mathematically, developing equations in the early 1820s with extraordinary speed and precision. The English experimentalist Michael Faraday had shown how changing magnetic fields create electric fields, demonstrating electromagnetic induction in 1831 through elegant tabletop experiments using coils and magnets. All of these phenomena were being catalogued, measured, and connected by researchers across Europe throughout the first half of the 19th century. But nobody had written them all down as a single, unified mathematical system that captured all of electricity and all of magnetism together in one coherent framework. Maxwell did that. Between 1861 and 1865, he published a set of equations, just 4 of them, that described everything electricity and magnetism could do. Every electric field, every magnetic field, every interaction between the two, every wave, every force, every induction, every capacitor, every transformer, every electromagnet ever built or imagined, all governed by those 4 compact mathematical statements. And then, Maxwell did something that changed physics forever. He looked at what those four equations implied when you combined them and searched for wave-like solutions. When you have a changing electric field, it creates a changing magnetic field. When you have a changing magnetic field, it creates a changing electric field. Those two changes feeding each other indefinitely. An electric field oscillating produces a magnetic field oscillating, which produces an electric field oscillating, which produces a magnetic field oscillating. On and on, across space, without any wire, without any material medium, without anything to carry the wave except the fields themselves. A self-sustaining oscillation propagating through open space. A wave. Maxwell worked out the mathematics of that wave with great care. He calculated how fast it would propagate through the vacuum, using only two constants that had already been measured in laboratories entirely independently of any work on light or optics. One constant described how strongly electric fields form in a vacuum, a quantity physicists call the permittivity of free space. The other described how strongly magnetic fields form in a vacuum, a quantity called the permeability of free space. Both had been measured experimentally by researchers working on electricity and magnetism. Both were numbers that physicists already had written in their notebooks. Neither had anything to do with optics. Neither had anything to do with light. Maxwell plugged those numbers into his formula for the speed of his electromagnetic wave. The result came out to approximately 300 million meters per second, and Maxwell recognized that number immediately. Because the speed of light had already been measured. The Danish astronomer Ole Rømer had estimated it in 1676 by watching the orbital timing of Io, one of Jupiter's moons. He noticed that Io's eclipses behind Jupiter appeared to run late when Earth was moving away from Jupiter in its orbit, and ran early when Earth was approaching Jupiter. Rømer concluded that the discrepancy was because light took time to travel the varying distance between Earth and Jupiter, and the travel time changed as that distance changed over the course of Earth's orbit. He estimated the speed at roughly 220,000 kilometers per second. Not perfectly accurate, but astonishingly close for a 17th century measurement made entirely from planetary observations. No laboratory equipment involved at all. Later measurements refined the number considerably. In 1878, Albert Michelson measured it with unprecedented precision using a rotating mirror apparatus set up at the United States Naval Academy in Annapolis. He spent years refining the technique, eventually moving his apparatus to longer baselines in California, achieving accuracy within a tiny fraction of a percent of the modern accepted value. He would devote most of his career to this number, returning to it again and again with increasingly sophisticated equipment. By Maxwell's time, physicists had a reliable value for how fast light moved, about 300 million meters per second. The same number Maxwell got from combining two constants of electricity and magnetism that had been measured separately in completely different kinds of experiments by completely different people working on completely different problems. Identical. Maxwell wrote in his 1865 paper that the agreement of the results seemed to show that light and the electromagnetic medium were one and the same. Light was not something separate from electricity and magnetism. Light was an electromagnetic wave, a ripple in electric and magnetic fields propagating through the vacuum, carrying energy and information at a speed determined entirely by how the vacuum responds to those fields. And the speed of light was not arbitrary or mysterious. It fell directly out of those two laboratory-measured constants: the permittivity of free space and the permeability of free space, two numbers measured with capacitors and coils. Combined, according to Maxwell's formula, out comes the speed of light. This is one of the great revelatory moments in the history of science. Three apparently separate phenomena, electricity, magnetism, and light, turned out to be aspects of a single unified theory, and the speed of light fell out of that unification without anyone having to put it in. It was a prediction that emerged from the mathematics, checked against what astronomers had already measured, and found to match. So the question shifts. If the speed of light comes from those two constants, what determines the values of those constants? This is where things get genuinely strange. The permittivity of free space tells you how much electric field you get in response to a charge placed in a vacuum. How easily, in other words, the vacuum allows an electric field to form and propagate. It has a value of approximately 8.85 times 10 to the power of minus 12 farads per meter. That number is not derived from something deeper, at least not within classical electromagnetism. It is a property of the vacuum itself. A fact about empty space. The permeability of free space tells you how much magnetic field you get from a current flowing in a vacuum. How easily the vacuum allows a magnetic field to form and propagate. It has a value of approximately 1.26 times 10 to the power of minus 6 henries per meter, also a property of the vacuum. Together, they determine how freely electromagnetic fields can form and propagate in empty space. And together, through Maxwell's formula, they determine the speed of light. The actual calculation is clean. The speed of light equals 1 divided by the square root of the permeability of free space, multiplied by the permittivity of free space. Plug in the values. The result is approximately 299,792,458 meters per second. That is the speed of light. So in a very direct sense, the speed of light is determined by how easily the vacuum of this universe permits electric and magnetic fields to exist and propagate. A vacuum that resists electric and magnetic fields more strongly, with higher constants, would have a slower speed of light. A vacuum that allows fields to form more easily, with lower constants, would have a faster speed of light. Our universe has the particular vacuum properties it has. And so, our speed of light is what it is. But that answer immediately creates another question. What exactly is the vacuum? You might think the vacuum is nothing. The absence of everything. A perfect void where there are no particles, no fields, no energy. And you would be wrong. This is one of the most important and counterintuitive discoveries of 20th century physics. Quantum mechanics, developed through the 1920s and 1930s, revealed something deeply unsettling about empty space. The vacuum is not empty. It is the lowest energy state of every quantum field that exists in nature. But lowest energy does not mean zero energy. This is where the Heisenberg uncertainty principle becomes important. Heisenberg's principle is often stated as a relationship between position and momentum. The more precisely you know where a particle is, the less precisely you can know how fast it is moving, and vice versa. But it applies equally to energy and time. The more precisely you know the energy of a system over a given time interval, the less precisely you can know the time at which it has that energy. Another way to say it, the shorter the time interval you observe, the greater the energy, uncertainty, in that observation. If the electromagnetic field in the vacuum were exactly zero everywhere, always, its energy would be exactly zero, perfectly known at every moment. Heisenberg's principle forbids this. The energy cannot be exactly zero. It must fluctuate. The field value at every point in space is perpetually uncertain. Virtual pairs of particles and antiparticles constantly pop into and out of existence, borrowing energy from the vacuum and returning it before any long-term imbalance accumulates. These are called quantum vacuum fluctuations or zero-point fluctuations, and they are not theoretical bookkeeping. They are real, and they produce measurable physical effects that have been confirmed in the laboratory to extraordinary precision. The Casimir effect is the most direct demonstration. Imagine two uncharged, perfectly flat, perfectly parallel metal plates placed very close together in a vacuum. Nothing electrically connects them. No charge sits on either one. No magnetic field acts between them. No macroscopic force of any kind. Yet the plates attract each other. The reason is that the quantum vacuum fluctuations between the plates are different from the fluctuations outside the plates. The plates are conductors. That means the electric field must be exactly zero at their surfaces. This imposes a boundary condition on the electromagnetic vacuum fluctuations in the gap. Only fluctuations with wavelengths that fit an integer number of times into twice the gap can exist inside. Longer wavelengths cannot fit. Outside the plates, no such restriction applies. All wavelengths are permitted. The result is that there are fewer electromagnetic modes, fewer ways for the vacuum to fluctuate between the plates than there are outside. The vacuum has lower energy density between the plates than outside. This energy mismatch produces a real force, a net inward pressure pushing the plates together. The Casimir effect was predicted by the Dutch physicist Hendrik Casimir in 1948, working through the mathematics of the zero-point energy of the electromagnetic vacuum. It was measured experimentally, first roughly in the 1950s, and then, with high precision, by the physicist Steve Lamoureux in 1997. The force between the plates depends on their separation and their area. At a separation of 1 micrometer, the Casimir pressure is about 1 pascal. Not large, but entirely measurable and fully consistent with the theoretical prediction. Since then, the effect has been confirmed in many configurations between spheres and flat plates, between different materials, with plates made of different metals. Every measurement confirms the same picture. The vacuum has energy. It has structure. It has physical effects. It is not nothing. And those properties, specifically the permittivity and permeability of free space, which quantify how the vacuum responds to electromagnetic fields, are what set the speed of light. There are other demonstrations of vacuum structure. One of the most famous is the anomalous magnetic moment of the electron. In quantum mechanics, every electron has an intrinsic property called spin, which gives it a magnetic moment, a way of interacting with magnetic fields. The basic prediction from quantum mechanics for the size of this magnetic moment gives a specific numerical value. But when physicists measured the actual magnetic moment very precisely, they found it differed from that basic prediction by a tiny amount. Not much, but consistently. The correction is about 1 part in 1,000. The full calculation, using quantum electrodynamics, the quantum theory of the electromagnetic force, accounts for the correction by including the effects of virtual particles. The electron constantly emits and reabsorbs virtual photons. It briefly splits into a virtual electron and a virtual photon and recombines. These fluctuations, the quantum vacuum seething around the electron, slightly modify its magnetic moment. When those corrections are calculated using quantum electrodynamics, the prediction matches the measured magnetic moment to 11 decimal places. 11 decimal places. This is the most precisely confirmed theoretical prediction in the history of science. And it works because the vacuum is real. Its fluctuations have real consequences, and quantum electrodynamics describes those consequences correctly. The same quantum vacuum, whose structure sets the permittivity and permeability of free space, is the vacuum whose fluctuations correct the magnetic moment of the electron to 11 decimal places. The vacuum is physical. Its properties are measurable, and one of its properties is the speed of light. Albert Einstein took Maxwell's work and followed it somewhere nobody expected. In 1905, the same year he published the paper explaining the photoelectric effect that would eventually win him the Nobel Prize, and the paper that would eventually lead to the understanding of Brownian motion, he published what would become the special theory of relativity. He was not thinking primarily about what determines the speed of light. He was thinking about a deep inconsistency that had been quietly troubling physicists for nearly 20 years. Maxwell's equations gave a specific speed for electromagnetic waves in a vacuum. But speed relative to what? In everyday life, speeds are always relative to something. A train moves at 200 kilometers per hour relative to the ground. A plane moves at 900 kilometers per hour relative to the air, and somewhat different relative to the ground depending on the wind. Every speed is a comparison between two things. But Maxwell's equations gave the speed of light with no reference frame attached. Not relative to the source of the light. Not relative to any medium. Just a speed, standing alone, the same regardless of what the source was doing. This made no sense under Newtonian physics, where velocities always add and subtract depending on your frame of reference. If you're on a train moving at 100 kilometers per hour and you throw a ball forward at 50 kilometers per hour relative to yourself, someone standing on the platform sees the ball moving at 150 kilometers per hour. Speeds add. Simple arithmetic. But if the same arithmetic applied to light, then light emitted from a moving source should travel at different speeds in different directions as seen by a stationary observer. And experiments were showing no such effect existed. The most thorough test was the Michelson-Morley experiment of 1887. Albert Michelson, the same physicist who had measured the speed of light so carefully, and Edward Morley built an exceptionally sensitive device. An interferometer that split a beam of light into two perpendicular paths, sent each path to a mirror and back, then recombined the beams. If light moved at slightly different speeds in different directions, the two recombined beams would be slightly out of phase, producing a shifted interference pattern. The device was sensitive enough to detect the expected effect if it was there. Michelson and Morley measured. They rotated the apparatus. They repeated at different times of day as Earth rotated, changing the direction of the apparatus relative to Earth's orbital motion. They repeated at different times of year as Earth moved in different directions around the Sun. They found nothing. No shift. No difference in speed. The speed of light was the same in every direction. This result baffled physicists. The problem sat unresolved for almost 2 decades. Some proposed that moving objects physically contract in the direction of motion by just enough to cancel the expected effect. The Dutch physicist Hendrik Lorentz and the Irish physicist George Fitzgerald independently developed the mathematics of this contraction. It gave the right numerical answer, but it felt contrived. A fix invented specifically to explain away an inconvenient result. Einstein did something different. He took the experimental result at face value and followed the logic without flinching. He proposed two postulates. First, the laws of physics are the same for all observers in uniform motion relative to each other. An experiment conducted on a smoothly moving ship gives the same results as the same experiment in a stationary laboratory. Second, the speed of light in a vacuum is the same for all such observers, regardless of the motion of the source or the observer. Not roughly constant. Not constant within experimental precision. Exactly constant for every observer in every state of uniform motion. This sounds simple. The implications are anything but. If you are in a spacecraft moving at half the speed of light relative to Earth, and you shine a flashlight forward, the light from that flashlight does not move at 1.5 times the speed of light relative to Earth. It moves at exactly the speed of light. The same 299,792,458 meters per second that a stationary observer on Earth would measure. How can both observers measure exactly the same speed for the same light beam? The answer is that space and time are not rigid fixed structures against which motion happens. They are malleable. Space and time themselves stretch and compress in ways that depend on the observer's state of motion. An observer in the spacecraft and an observer on Earth disagree about how long a given event took. They disagree about how far apart 2 points are, but they agree on the speed of light. Their disagreements about space and time are precisely calibrated to guarantee this agreement. Time runs at different rates for observers in relative motion. This is not a perceptual illusion. It is not that moving observers merely think time is running slower. It actually runs slower. Atomic clocks placed on fast-moving aircraft have been compared to identical clocks left on the ground. The airborne clocks lose time, precisely the amount special relativity predicts. The effect is tiny for the speeds of aircraft, measured in nanoseconds. But it is real. GPS satellites move at roughly 14,000 kilometers per hour in their orbits. The time dilation this produces is small, but not negligible. Without continuous correction for relativistic effects, GPS position estimates would accumulate errors of kilometers every day. The correction is built into the system. Without it, GPS navigation would not work. Time dilation is not a curiosity. It is a practical engineering consideration in the most widely used navigation technology on Earth. Lengths also depend on the observer. An object moving at high speed is contracted along its direction of motion when measured by a stationary observer. Space and time are not two separate, independent backgrounds. They are aspects of one unified structure that Einstein called spacetime. And the speed of light is not just the speed of light. It is the conversion factor between space and time. The exchange rate between two quantities that turn out to be aspects of the same thing. When you write E equals mc squared, the c in that equation is this conversion factor. A tiny amount of mass is equivalent to an enormous amount of energy, because c is large and c squared is enormous. 299,792,458 meters per second multiplied by itself. That is a staggering multiplier. It means matter and energy are not fundamentally different things. They are the same thing, expressed differently. Mass is a form of energy. Energy has an equivalent mass. The conversion factor between them is the square of the speed of light. Every nuclear weapon, every nuclear reactor, every star runs on that relationship. The Sun converts about 4 million metric tons of mass into energy every second through nuclear fusion. 4 million metric tons of matter converted to pure energy every second. The Sun has been doing this for 4.5 billion years. It will continue for another 5 billion before its hydrogen runs low. The reason a star can burn for 10 billion years is the size of c². The energy density locked in mass at the exchange rate set by the speed of light is large enough to sustain stellar luminosity for timescales that dwarf the history of life on Earth. Now pull back even further. Special relativity reveals something profound about the geometry of the universe. In spacetime, there is a mathematical object called the spacetime interval. It is a way of measuring the separation between any two events, mixing space and time together in a specific ratio. The spacetime interval squared equals the distance in space squared minus the speed of light squared times the time elapsed squared. That minus sign is critical. Space and time do not add together the way two perpendicular spatial distances do. They enter the formula with opposite signs. And the coefficient connecting them is the speed of light squared. This means the speed of light is not simply a property of electromagnetic waves. It is a property of the geometry of spacetime itself. It appears in the spacetime metric, the mathematical object that defines what distance and duration mean throughout the universe. Change the speed of light, and you do not just change how fast light moves. You change the geometry of spacetime. You change the relationship between cause and effect. You change what it means for two events to happen simultaneously for different observers. You change how forces propagate. You change how gravity works. The speed of light is not a parameter that sits inside physics alongside the geometry of spacetime. It is baked into the geometry itself. This is why physicists sometimes say that the speed of light is not really a property of light. Light happens to travel at c because photons are massless. But c itself is a property of the universe's structure. A universe without light would still have c. It would be the maximum speed at which any influence, any particle, any signal of any kind could propagate. Because it is written into the metric of space-time. There is something stranger still. The speed of light is not just a speed limit for light. It is the speed limit for causality. Nothing can travel faster than c. Not matter. Not energy. Not information. Not gravity. Not any physical influence of any kind. This is not a technical limitation that might be overcome with better engineering. It is a consequence of the logical structure of space-time. To see why, think about what faster-than-light travel would mean for cause and effect. In relativity, two observers in relative motion can disagree about the sequence of events that are widely separated in space. For events where one cannot physically reach the other by traveling at the speed of light or slower, different observers can legitimately disagree about which came first. One observer says, "Event A came first." Another observer, moving in a different direction, says event B came first. Both are internally consistent. And this is fine, because for those events, one cannot cause the other. Nothing moving at or below C can get from event A to event B, or from B to A. So no physical cause and effect chain can connect them. The ordering between them has no physical significance. Causality is preserved precisely because nothing can travel fast enough to connect them. Now imagine something that could travel faster than C. It could connect those events. In one reference frame, you send a signal from event A to event B, forward in time. In another reference frame, moving in the right direction, at the right speed, that same signal was sent backward in time, from the future to the past. If you then use two such signals, one in each reference frame, you could in principle transmit information back to a time before you sent it. You could receive a reply before you sent the question. You could violate causality. The logical structure of cause and effect would collapse. The speed of light is not just about how fast light moves. It is the maximum speed at which any cause can produce any effect. It is the speed of causality. Remove that limit, and the universe loses its logical coherence. Now consider what physicists call the fine structure constant. It carries the symbol alpha, and it is one of the most important numbers in all of physics. Its value is approximately 1 over 137. More precisely, about 0.0072973. This number is dimensionless. It has no units. Not meters per second, not kilograms, not anything. A pure number. A pure ratio. The fine structure constant is built from three other fundamental constants of nature combined in a specific way. The elementary charge of the electron, the speed of light, and Planck's constant, which sets the scale of all quantum effect. Combined in the right ratio, the units cancel completely. What you are left with is a dimensionless number that compares the strength of the electromagnetic interaction to the quantum scale. The fine structure constant tells you how strongly electrically charged particles interact with photons, how tightly electrons are bound in atomic orbitals around nuclei. The sizes of those orbitals depend on it. A larger fine structure constant would mean electrons bound more tightly in smaller orbits. A smaller fine structure constant would mean they are bound more loosely in larger orbits. The energies at which atoms absorb and emit light depend on it directly. The characteristic colors of light emitted by different elements, the spectral fingerprints that astronomers use to identify what distant stars are made of, are all determined by the fine structure constant. Every chemical bond depends on it. Every molecule owes its stability and properties to the fine structure constant. The structure of DNA depends on it. The folding of proteins depends on it. The function of enzymes depends on it. The rate of metabolic reactions depends on it. The firing of neurons depends on it. The fine structure constant was the obsession of the theoretical physicist Wolfgang Pauli, who spent years trying to derive its value from some deeper principle and never succeeded. It is said he wanted nothing more than to understand why that pure number was approximately 1 over 137 before he left this world. The question haunted him because that number cannot be derived from any deeper theory we have. It is simply measured, and the fine structure constant is tied directly to the speed of light. Change c while holding the electron charge, and Planck's constant fixed, and the fine structure constant changes. Change it enough, and atomic physics changes. Change atomic physics, and chemistry changes. Change, chemistry, and biology becomes impossible. The universe is exquisitely sensitive to the exact value of the speed of light, not because light is special, but because c is woven into atomic physics through the fine structure constant, which governs the chemistry that every living thing depends on. Maxwell found light in the equations of electricity and magnetism. Einstein found space and time in the constancy of light's speed. Quantum mechanics found structure in the vacuum that should, according to classical physics, be empty. Each discovery revealed the speed of light to be more deeply embedded in the structure of reality than the previous one had shown. The pattern is consistent. Every time physicists thought they understood where c came from, the next generation of theory showed it sitting at a deeper level than anyone had realized. And that pattern has continued. In the 1940s and 50s, physicists developed quantum electrodynamics, QED for short. This is the quantum theory of the electromagnetic force. It describes how electrons interact with photons, how electric and magnetic fields arise from the quantum behavior of charged particles, and how light is emitted and absorbed by matter. QED is built on the principles of both quantum mechanics and special relativity. It is a relativistic quantum field theory, and c appears in it at every level. In the relativistic wave equation for the electron, the Dirac equation, c enters explicitly. In the equations describing how photons propagate, c appears. In the interaction terms, c appears. The theory is saturated with c, and QED is extraordinarily accurate. Its predictions for the magnetic moment of the electron match measurements to 11 decimal places. Its predictions for the energy levels of hydrogen match observations with similar precision. It predicted that pairs of particles and antiparticles could be created from pure electromagnetic energy if that energy exceeded a threshold set by c. The threshold energy equals twice the particle mass times c squared. This process was confirmed experimentally. QED predicted that an electron and its antiparticle, the positron, could briefly pair up and orbit each other in a system called positronium, with specific energy levels and a specific decay rate into photons. All of this was confirmed. QED is the most precisely tested theory in science, and c is embedded in it at every level. In the 1960s and 70s, physicists achieved something extraordinary. They unified two of the four fundamental forces of nature into a single theoretical framework. The electromagnetic force and the weak nuclear force were shown to be two aspects of a single underlying force called the electroweak force. At the energies we encounter in everyday life, and even in most laboratory experiments, they look completely different. Electromagnetism acts over infinite distances, holding atoms together and driving chemistry. The weak nuclear force acts only over distances smaller than an atomic nucleus and is responsible for certain types of radioactive decay. They seem like completely different things. But at energies above, about 100 times the mass of the proton, they merge into a single force with a single underlying symmetry. The physicists Sheldon Glashow, Abdus Salam, and Steven Weinberg developed this unification in the 1960s and shared the Nobel Prize in Physics in 1979. The electroweak theory predicted the existence of three new particles that should be the carriers of the weak force. Two charged particles called the W bosons and one neutral particle called the Z boson. The theory specified their masses with precision. They were discovered at CERN in 1983 at exactly the predicted masses. This was one of the greatest confirmations of a theoretical prediction in the history of physics. And within the electroweak theory, the speed of light is built in throughout. It appears in the relationship between the electromagnetic and weak coupling constants. It appears in the masses of the W and Z bosons. It appears in every calculation. When you change C in the electroweak theory, you change the masses of the W and Z bosons. You change the rate of nuclear reactions. You change the lifetime of particles. You change the rate of radioactive decay. The speed of light is not peripheral to particle physics. It is structural. In the 1980s and 1990s, particle physicists discovered the Higgs mechanism. The question they were trying to answer was, why do the W and Z bosons have mass? In the electroweak theory, as originally written, gauge symmetry requires all the gauge bosons to be massless. The photon is massless. That is consistent. But the W and Z bosons are not massless. Their masses were measured at CERN in the 1980s. How do particles get mass while the underlying symmetry requires them to be massless? The answer was proposed in the 1960s by several physicists, including Peter Higgs, François Englert, Robert Brout, Tom Kibble, Gerald Guralnick, and Carl Hagen. The mechanism is as follows. There is a quantum field that fills all of space. In the vacuum, this field does not sit at zero. It sits at a non-zero value. The vacuum state has a non-zero value for this field everywhere in the universe. Particles that interact with this field acquire mass from that interaction. The stronger the interaction, the greater the mass. The W and Z bosons interact strongly with the Higgs field and acquire large masses. The photon does not interact with the Higgs field at all. The gauge symmetry of electromagnetism protects the photon from acquiring mass. And because the photon is massless, it must travel at exactly c. The Higgs boson, the quantum of the Higgs field, was predicted to exist as a consequence of the mechanism. It was searched for decades. Finally, on July 4, 2012, physicists at CERN announced its discovery. The Higgs boson was found with a mass of approximately 133 times the mass of the proton, within the range the Standard Model had allowed. The discovery confirmed the entire mechanism. It confirmed that the photon's masslessness is protected by gauge symmetry. It confirmed that the vacuum has a non-zero Higgs field filling all of space. And it confirmed that the structure of the vacuum, not just the electromagnetic vacuum, but the full quantum vacuum of all the Standard Model fields, is what gives particles their properties, including the photon, including masslessness, including the requirement to travel at c. The Standard Model of particle physics, which includes the electroweak theory, quantum electrodynamics, and quantum chromodynamics, the theory of the strong nuclear force, is one of the most successful theories in the history of science. It has made precise predictions that have been confirmed in laboratory after laboratory. The W and Z bosons were found where predicted. The top quark was found at Fermilab in 1995, at the mass the theory required. The Higgs boson was found at CERN in 2012 within the predicted range. Calculations within the Standard Model match measurements to 10 or 11 decimal places in the best cases. No theory in history has been tested more precisely. And yet, the Standard Model is not the final word. It does not include gravity. It does not explain dark matter, the invisible mass that outweighs all visible matter in the universe by a factor of about 5 to 1. It does not explain dark energy, the mysterious quantity causing the expansion of the universe to accelerate. It does not explain why there is more matter than antimatter in the universe. And it does not explain why its own parameters have the values they have. The masses of the quarks, the mixing angles between particle families, the strength of the strong nuclear force, the fine structure constant, the speed of light. There are about 20 free parameters in the standard model, 20 numbers you cannot calculate from within the theory. You measure them and insert them. The speed of light is one of them. Not because it is poorly understood, because even our best theories do not derive it from anything deeper. It sits at the bottom of the theory as a given. String theory is the most extensively developed attempt to go below the standard model. The core idea is that the fundamental objects in nature are not point particles, but tiny oscillating strings. Strings so small they are effectively point-like at any scale we can probe, but strings nonetheless. Different vibrational modes of these strings correspond to different fundamental particles. Different frequencies, different particles. Different patterns of oscillation, different properties. In this framework, the constants of nature are not free parameters you insert by hand. They are determined by the geometry of the universe at very small scales. String theory requires extra spatial dimensions beyond the 3 we experience. In most versions, the universe has 10 spatial dimensions or more. We live in 3 of them. The others are compactified, curled up at scales so small they are invisible to any instrument we have, perhaps at the Planck scale. The size and shape of those compactified dimensions determines the constants of nature. It determines the masses of particles. It determines the coupling strengths of forces. It determines the fine structure constant. It determines the permittivity and permeability of free space. And therefore, it determines the speed of light. Different geometries of the extra dimensions give different constants, different speeds of light, different universes. The problem is the enormous number of possible geometries. Estimates suggest there may be 10 to the power of 500 or more different consistent configurations of the extra dimensions in string theory, possibly many more. Each gives a different set of physical constants. Each gives a different universe. Which one is ours? String theory does not currently have a method to answer that. It has not yet predicted the speed of light from first principles. The constants of nature remain, in string theory, something determined by which vacuum our universe settled into after the Big Bang, not something uniquely predicted by the theory. Some physicists find this troubling. Others see it as a reflection of the actual structure of the multiverse. But the prediction of C from first principles remains out of reach for now. Loop quantum gravity takes a different approach. Instead of treating matter as strings, it tries to quantize space-time itself, to treat the geometry of space and time as a quantum object, subject to uncertainty, subject to discreteness at the smallest scales. In loop quantum gravity, space is not a smooth, continuous fabric. At the Planck scale, it is built from discrete quanta, tiny chunks of space and time, below which nothing smaller has meaning. The Planck length is approximately 1.6 times 10 to the power of minus 35 meters. The Planck time is approximately 5.4 times 10 to the power of minus 44 seconds. These are the scales at which spacetime would show its quantum nature if loop quantum gravity is correct. At these scales, the smooth, geometric description of general relativity breaks down. Space and time are no longer a classical background. They are quantum objects with their own dynamics. In this framework, the speed of light might not be an input. It might be a consequence. A property that emerges from the quantum structure of spacetime at larger scales. This is speculative. Loop quantum gravity has not yet made confirmed, precise predictions about any measured quantity, but the program points towards something meaningful. A future in which the speed of light is derived from the structure of space and time, rather than being measured and inserted. There is an experiment that illustrates the relationship between the vacuum and the speed of light in a way that is almost poetic. You can slow light down, not in a vacuum. Light in a vacuum always moves at exactly c. But light traveling through a material slows down. In glass, light moves at about 200 million meters per second. In water, at about 225 million meters per second. In air, barely slower than the vacuum. In diamond, at about 124 million meters per second. Less than half its vacuum speed. The reason is that the electromagnetic wave of light interacts with the atoms of the material. The photons are absorbed by atoms and re-emitted. Absorbed and re-emitted again. Each cycle takes a small amount of time. The average progress of the light pulse through the material is therefore slower than its speed in the vacuum between atomic interactions. This slowing is quantified by the index of refraction. Glass has an index of refraction of about 1.5, meaning light moves through it at about 2/3 of c. In the 1990s and 2000s, physicists realized they could push this much further using specially prepared quantum systems. Atoms cooled to within a tiny fraction of a degree above absolute zero, using laser cooling and magnetic trapping techniques, can be manipulated into quantum states that interact with light in extreme ways. In 1999, the physicist Lene Howe and colleagues at Harvard used a cloud of sodium atoms cooled to about 50 billionths of a degree above absolute zero. They sent a light pulse into this ultra-cold gas. The pulse slowed, not to 2/3 of c, not to 1,000th, to 17 meters per second. 17 meters per second. A fast cyclist can match that speed. Later, the same group slowed it further, and then stopped it entirely. A pulse of light was frozen in the atomic cloud. Its information transferred to the quantum state of the atoms. Held there. Then, by reapplying the right laser fields, released again as light. Light, stopped, held, and released. This does not violate any principle of physics. The photons between atoms were still moving at c. But the information, the pattern that constitutes the light pulse, was stored as quantum state of the atoms and then converted back to light. The experiment makes the key distinction viscerally clear. The speed of light in materials is not c. It can be anything, even zero, with the right material. What is always c is the speed of light in a true vacuum. The speed set by the electromagnetic properties of the vacuum itself. That speed is not negotiable. It is not something materials can change. It is the speed of electromagnetic propagation through a quantum vacuum whose properties are fixed by the universe's structure. The question of whether the speed of light has always been the same is not considered controversial within mainstream physics, but it has been seriously examined. In the late 1990s, the physicists João Magalhães and Andreas Albrecht proposed a theory in which c was much larger in the very early universe and decreased over time. They were motivated by cosmological puzzles, specifically the horizon problem. The cosmic microwave background radiation is the thermal afterglow of the early universe, released about 380,000 years after the Big Bang, when the universe cooled enough for electrons and protons to combine into neutral hydrogen. This radiation fills the sky. It is almost perfectly uniform in temperature. The temperature varies by only about 1 part in 100,000 from one direction to another. But the regions of the sky we observe in opposite directions are separated by distances so large that, in standard cosmology, light would never have had time to travel from one side to the other since the Big Bang. They should be out of causal contact. They should not have the same temperature. But they do. The mainstream solution is cosmic inflation. A period of exponential expansion in the first fractions of a second after the Big Bang, during which a tiny, causally connected region was stretched to scales larger than the current observable universe. Everything we see today descended from that small connected patch, which is why it all looks the same. The varying speed of light theory was an alternative. If c was much larger in the early universe, causal influences could have spread across larger distances. The uniformity of the cosmic microwave background would then be natural, even without inflation. The theory made cosmological predictions. It was compared to observations. It did not match as well as inflation. It remained a minority view. But the fact that it was taken seriously and rigorously developed shows something important. The speed of light is not treated by physicists as sacred. It is not assumed to be eternal and unchanging. It is treated as a measurable quantity that could, in principle, have had a history. So far, the evidence says it has been essentially constant for the age of the observable universe. But that is an observational conclusion, not an assumption. Observations of very distant quasars have been used to test whether the fine structure constant, and therefore the speed of light, has varied over cosmic history. A quasar is a galactic nucleus powered by a supermassive black hole accreting material. They are among the most luminous objects in the universe. Some quasars are so distant that the light we observe left them more than 10 billion years ago. The light from quasars passes through clouds of gas between the quasar and us. Those gas clouds leave absorption lines in the quasar's spectrum, lines at wavelengths set by the physics of hydrogen and other elements. The positions of those absorption lines depend on the fine structure constant. If the fine structure constant was different 10 billion years ago, the absorption lines would be at slightly different positions than the same lines produced by the same elements in laboratories on Earth today. The comparison between ancient and modern spectra tests whether the constants have changed. Several research groups have carried out this comparison using large telescopes. Some have reported possible small variations. Others have not confirmed them. The current best estimates suggest that if the fine structure constant has varied over the last 10 billion years, it has done so by no more than a few parts per million. Essentially constant, but with the constraint coming from observation rather than assumption. The fact that astronomers can test this at all, by comparing ancient light from distant quasars to laboratory measurements here on Earth, is remarkable. It means the speed of light, through the fine structure constant, is something the universe has been testing for us across cosmic history. Something quietly remarkable happened in 1983 that reflects just how fundamental the speed of light is. The International Bureau of Weights and Measures redefined the meter. For most of modern history, the meter was defined by reference to physical objects or natural phenomena. At various times, it was defined as 1/10,000,000th of the distance from the North Pole to the equator along a particular meridian, or as the length of a particular metal bar kept in France, or as a certain number of wavelengths of a specific light source. In 1983, the definition changed. The meter was defined as the distance light travels in a vacuum in exactly 1,299,792,458th of a second. This is not a measurement. It is a definition. By this definition, the speed of light is now exactly 299,792,458 meters per second. Not approximately. Exactly. No uncertainty. If you ask whether the speed of light is changing, you have to be careful. If the meter is defined in terms of the speed of light, then by definition, the speed of light in meters per second cannot change. We have defined it that way. What might change, what we could actually detect, is whether the fine structure constant changes, or whether the ratio of the speed of light to other physical quantities shifts in a way that produces observable effects on atomic spectra or other measurable quantities. The choice to define the meter using C was not arbitrary convenience. It reflects the fact that C is the most stable, reproducible, universal physical constant we have access to. Light in a vacuum always moves at C, everywhere in the universe, at all times so far measured. No material artifact can match that stability. No natural frequency, even a highly stable atomic transition, is quite as universally constant. C anchors our measurement system because it is the most fundamental thing in the system. Now think about what a photon actually experiences, if experience is even a meaningful concept for a massless particle. Special relativity tells us what happens to time for observers in motion. As an observer moves faster, their clock, from the perspective of a stationary observer, runs slower. This is time dilation. It has been measured precisely. Muons, unstable subatomic particles created when cosmic rays strike the upper atmosphere, travel downward at close to the speed of light. Their internal decay rate is a kind of clock. Measured in the lab, a muon decays in about 2 microseconds. But muons, produced at high altitudes in the atmosphere, traveling at close to C, reach the surface of Earth before decaying, even though the journey should take longer than their lifetime. If you use the 2 microsecond figure, the reason is time dilation. From the muon's perspective, the atmosphere is contracted and the journey is short. From our perspective on Earth, the muon's clock runs slow and its lifetime is extended. Both descriptions give the same physical outcome. The muon reaches the surface. We can detect it. This happens continuously. Muons from cosmic rays are reaching the surface of Earth right now. Their survival is a direct verification of relativistic time dilation. Now carry that logic to its limit. At the speed of light, time dilation is infinite. from the frame of a photon. If such a frame could exist, no time passes at all between emission and absorption. The moment a photon is created by an electron dropping to a lower energy level in some distant star, and the moment it strikes your retina are the same moment. From the photon's perspective, no journey, no duration, just an instantaneous connection between 2 points in space-time. The caveat is that a photon technically has no rest frame. You cannot define a reference frame for a massless particle. The notion of what the photon experiences is mathematically undefined in special relativity. But the limit, as you approach c, points towards something striking. Time slows. Space contracts along the direction of travel. At exactly c, both go to zero. The universe of a photon, if it could be experienced, would be a single point in space and a single instant in time. Everything compressed to nothing. Duration and distance abolished. The ancient light, arriving in your eye from a star 1,000 light-years away, left that star 1,000 years ago in your reference frame. In some sense, the photon does not know the difference. The story of how we measured the speed of light is itself worth understanding, because each method of measurement reveals something different about what the speed of light actually is and where it comes from. Romer's measurement in 1676 was purely astronomical. He was watching the moons of Jupiter through a telescope. He wasn't trying to measure the speed of light. He was trying to make astronomical tables more accurate. The timing of Io's eclipses was used by sailors to set their clocks, which they needed to determine longitude at sea. Accurate timing meant accurate navigation, and the timing was off. Io would emerge from Jupiter's shadow a few minutes late or a few minutes early, depending on the time of year. Romer figured out the discrepancy. Light had a finite speed, and the changing distance between Earth and Jupiter meant the light took varying amounts of time to cross that gap. He estimated the speed at about 220,000 kilometers per second. The correct value is about 300,000 kilometers per second. Romer was off by about 25%. But the key insight was right. Light was not instantaneous. It had a speed. That was not at all obvious at the time. Galileo had tried to measure the speed of light by having two observers with lanterns on hilltops send signals to each other. When one uncovered their lantern, the other was supposed to respond immediately. The delay between the first signal and the response would give the travel time of light over the known distance. The experiment failed. The reaction times of the observers were far longer than the travel time of light over any distance that could be covered by hilltops within sight of each other. Galileo concluded that if light had a finite speed, it was very large. Romer's method worked because Jupiter is very far away. Far enough that the travel time of light across the changing Earth-Jupiter distance is measurable in minutes. James Bradley found a different method in 1728. He discovered what is called stellar aberration. When Earth is moving in one direction in its orbit, a telescope has to be tilted slightly in that direction to catch the light from a star, the same way you have to tilt an umbrella forward in the rain when you're walking. The angle of the tilt depends on the ratio of Earth's orbital speed to the speed of light. Earth's orbital speed is known. Measure the angle of aberration and you can calculate the speed of light. Bradley got a value very close to the correct one, and his method was entirely different from Romer's. Both methods gave the same answer. That agreement was itself significant. It meant the speed of light was a real, consistent physical quantity, not an artifact of one particular measurement technique. Armand Hippolyte Louis Fizeau made the first laboratory measurement in 1849. He sent a beam of light through a gap in a rotating toothed wheel, out to a mirror 8 kilometers away, and back through the wheel. At the right rotation speed, the returning light would pass through the next gap instead of being blocked by a tooth. The rotation speed needed to achieve this gave the travel time of light over the round-trip distance. Fizeau got a value within about 5% of the correct answer. Jean-Bernard Léon Foucault refined the technique the next year using a rotating mirror instead of a toothed wheel, getting closer still. Michelson spent decades further refining the rotating mirror method, eventually setting up a measurement between two mountain peaks in California, Mount Wilson and Mount San Antonio, separated by about 35 kilometers. His final measurements in the early 1930s achieved precision within a few kilometers per second of the modern value. He used the time it took for light to make the round trip between the mountains to calculate the speed. He died in 1931 before the final results from his last experiments were published. But by then, the speed of light had been measured well enough to confirm Maxwell's theoretical prediction from the electromagnetic constants. The number fell out of electricity and magnetism. The number was confirmed by Romer's moons of Jupiter, by Bradley's tilting of telescopes, by Fizeau's spinning wheels, by Foucault's rotating mirrors, by Michelson's mountain peaks. The same number from completely different methods. That consistency is not a coincidence. It is the universe being uniform. The speed of light is the same everywhere. We can measure it. The same in all directions. The same at all times, so far tested. It is a constant in the most literal sense. The relationship between Maxwell's electromagnetic constants and the speed of light has a subtlety worth exploring. When Maxwell calculated the speed of electromagnetic waves, he found it equaled 1 divided by the square root of the permeability of free space times the permittivity of free space. But why those two constants? What do they actually represent physically? The permittivity of free space, epsilon sub 0, tells you about the electric susceptibility of the vacuum. Specifically, it tells you how much electric displacement you get per unit of electric field in a vacuum. If you set up a pair of parallel plate capacitors with a vacuum between them and charge them up, the permittivity of free space tells you how the electric field in the gap relates to the charges on the plates. A higher permittivity means the vacuum resists the establishment of an electric field more strongly. Or, looked at differently, a given charge arrangement produces a weaker electric field. The permeability of free space, mu sub 0, tells you about the magnetic susceptibility of the vacuum. If you run a current through a wire, the permeability of free space tells you how strong a magnetic field you get around the wire. A higher permeability means a given current produces a stronger magnetic field. Together, these two constants tell you how the vacuum responds to electromagnetic disturbances, how efficiently it supports electric fields, how efficiently it supports magnetic fields. And those efficiencies together determine how fast those fields can exchange energy back and forth as the electromagnetic wave propagates. The wave works by converting electric field energy into magnetic field energy and back again. Like a pendulum, converting kinetic energy to potential and back. The rate at which this conversion happens, set by the two constants, determines the speed of propagation. High permittivity makes the electric field component respond slowly. High permeability makes the magnetic field component grow quickly for a given current. Both constants combine to set the rate of oscillation of the electromagnetic wave, and the speed of the wave is set by that rate of oscillation relative to the wavelength. This is the physical content behind Maxwell's formula, and it reveals something. The speed of light is not just a number. It reflects how the vacuum stores and exchanges electric and magnetic energy. The vacuum has a kind of electromagnetic inertia and a kind of electromagnetic compliance. Those two properties together set the speed at which electromagnetic energy can move through it. The vacuum is not passive. It participates. One of the most striking implications of the speed of light connects to our ability to observe the universe. When you look at the night sky, you are not seeing the universe as it is. You are seeing it as it was. Light travels fast, but the universe is large. The moon is about 384,000 kilometers away, on average. Light from the moon takes about 1.3 seconds to reach Earth. When you see the moon, you are seeing it as it was 1.3 seconds ago. That's fine. 1.3 seconds is not a long time. The sun is about 150 million kilometers away. Light from the sun takes about 8 minutes and 20 seconds to reach Earth. When you see the sun, you are seeing it as it was over 8 minutes ago. If the sun were to somehow vanish right now, we would not know for 8 minutes. The nearest star, Proxima Centauri, is about 4.24 light-years away. When you look at Proxima Centauri, you are seeing it as it was 4.24 years ago. Alpha Centauri A, the nearest sun-like star, is about 4.37 light-years away. The star Sirius, the brightest star in the night sky, is about 8.6 light-years away. You are seeing it as it was 8.6 years ago. The Andromeda Galaxy, the nearest large spiral galaxy, is about 2.5 million light-years away. When the Hubble Space Telescope photographs the Andromeda Galaxy, it is seeing it as it was 2.5 million years ago. The most distant objects we can observe, the most remote quasars, are many billions of light-years away. When we detect their light, we are observing the universe as it was billions of years ago, when those objects were young. We cannot see the present state of any distant object. We always see the past. The further away an object is, the further back in time we are looking. The universe, as seen from Earth, is like a series of concentric shells in time. The closest objects are in the most recent past. The most distant objects are in the most ancient past. The observable universe has a fundamental limit set by the speed of light and the age of the universe. Light emitted at the moment of the Big Bang, about 13.8 billion years ago, has been traveling toward us ever since. The most distant light we can ever receive is the light that left its source when the universe was young enough for light to have just become free to travel. Before that, the universe was opaque, too hot, too dense for light to propagate freely. The cosmic microwave background radiation is this ancient light. It left its sources about 380,000 years after the Big Bang and has been traveling ever since. It is the oldest light we can observe. Everything before that is, in principle, inaccessible to observation through light. The speed of light, combined with the age of the universe, sets the horizon of what we can observe. The observable universe is not the entire universe. It is the sphere within which light has had time to reach us since the beginning. Beyond that sphere, the universe continues. But we cannot see it. Not because of technological limitations, because the universe has not existed long enough for light to travel from those places to here. The speed of light is not just a speed, it is a horizon, a boundary of knowledge, a limit on what the universe can tell us about itself within any given time. In 1865, Maxwell also made another prediction alongside the existence of electromagnetic waves. He predicted that electromagnetic waves would carry momentum. Light pushes on things. This seems strange. We do not feel pushed by sunlight when it falls on us. But the push is there. It is just very small. Maxwell derived the result from his equations. An electromagnetic wave carries momentum proportional to its energy divided by the speed of light. The force exerted on a surface by light is called radiation pressure. For ordinary illumination, it is tiny. But in space, where it can act over long periods without friction or other forces to compete with, it matters. The tails of comets are partly shaped by radiation pressure from the sun. When light hits a comet's nucleus and knocks off gas and dust, those particles are blown away from the sun. Not just because of the solar wind, the stream of charged particles from the sun, but because sunlight itself pushes on them. The tail always points away from the sun, regardless of the comet's direction of travel. The first person to observe the Gegenschein, a faint glow in the night sky visible in exactly the direction opposite the sun, was noting a manifestation of radiation pressure and the distribution of dust in the solar system. Spacecraft have been designed to use this pressure. The Japanese Aerospace Exploration Agency launched the Icaros spacecraft in 2010. It deployed a large, thin reflective sail and demonstrated propulsion by solar radiation pressure. The sail was about 200 square meters. The pressure produced was about 1/1,000,000th of a Newton. Tiny. But in space, with no friction, even a tiny sustained force accumulates. Over months, it produced measurable acceleration. The concept of solar sails for spacecraft propulsion uses the momentum of light. Light has momentum. Maxwell proved it, theoretically. It was confirmed experimentally in the 1900s. And it follows directly from the fact that electromagnetic waves carry energy at the speed of light. Energy divided by c gives momentum. The speed of light appears in the momentum of light as directly as it appears in E equals mc squared. The relationship between light and gravity deserves a deeper look. Einstein's general theory of relativity, which he completed in 1915, describes gravity not as a force, but as the curvature of spacetime produced by mass and energy. A massive object curves the spacetime around it. Other objects, moving freely through that curved spacetime, follow curved paths. What we call the gravitational pull of a massive object is really the curvature of spacetime, directing freely moving objects toward it. One of the first tests of general relativity was the bending of light by gravity. If spacetime is curved by mass, then light, traveling through curved spacetime, should follow curved paths. The path of a light ray from a distant star passing close to the sun should be bent toward the sun. From Earth, this would appear as a shift in the apparent position of the star. Newton's theory of gravity actually predicts a bending of light too, if you treat light as a stream of particles with effective mass given by their energy. But general relativity predicts exactly twice the bending that Newton's theory predicts. The difference is measurable. The opportunity to test it came in May 1919 during a total solar eclipse. During totality, the moon blocks the sun, and stars near the sun become visible. Arthur Eddington led an expedition to the island of Principe off the west coast of Africa to observe the eclipse. Another team went to Sobral in Brazil. They photographed stars near the sun during totality and compared the positions of those stars to photographs taken when the sun was not nearby. The stars appeared shifted by approximately 1.7 arcseconds. This matched the general relativistic prediction, not the Newtonian prediction. Einstein was right. Light bends in a gravitational field by exactly twice what Newton predicted. Gravity affects light. But light has no mass. Gravity is not pulling on its mass. It is curving the spacetime that light moves through. The light follows the curvature of spacetime. General relativity describes this mathematically by including the speed of light in the equations for how spacetime curvature affects the propagation of any signal. C appears in the geodesic equations of general relativity, in the way that gravity acts on light. In the Schwarzschild metric, which describes the geometry of spacetime around a massive body, like a planet or star. The speed of light again, woven into the geometry of curved spacetime. Not just flat spacetime, curved spacetime too. Black holes are the most extreme manifestation of this. A black hole is a region of spacetime where the curvature is so extreme that nothing, not matter, not radiation, not light, can escape once it passes inside the event horizon. The event horizon is not a physical surface. It is a boundary in spacetime. At the event horizon, the escape velocity equals the speed of light. Below the event horizon, the escape velocity exceeds the speed of light. Since nothing can travel faster than c, nothing that passes inside the event horizon can escape. The speed of light defines the event horizon. If the speed of light were different, black holes would be different. Their event horizons would be at different distances from the center. The temperature of Hawking radiation, the quantum radiation that black holes emit due to quantum effects near the event horizon, would be different. Everything about black holes is tied to c. The Schwarzschild radius, the radius at which an object of a given mass becomes a black hole, is equal to 2 times the gravitational constant times the mass divided by the speed of light squared. C squared in the denominator. A smaller c would mean a larger Schwarzschild radius. Objects of a given mass would become black holes more easily. A larger c would mean a smaller Schwarzschild radius. Objects of a given mass would need to be compressed more before becoming black holes. The structure of black holes, the relationship between their mass and the size of the region from which nothing can escape, is set by c. In our universe, the black hole at the center of our galaxy, Sagittarius A, has a mass of about 4 million times the mass of the Sun. Its event horizon has a radius of about 12 million kilometers, slightly less than the radius of our Sun. A supermassive black hole in a different universe with a different speed of light would have a different event horizon radius for the same mass. Everything scales with c. The detection of gravitational waves by LIGO in September 2015 was a landmark event. For the first time, physicists directly detected ripples in spacetime itself. The waves were produced by 2 black holes merging about 1.3 billion light-years away. The merger happened about 1.3 billion years ago. The gravitational waves spread outward from the merger at the speed of light. Not at the speed of sound. Not at some gravity wave speed. At the speed of light. Exactly, c. This was predicted by general relativity. Gravitational waves travel at the speed of light because they are disturbances in spacetime, and the maximum speed at which spacetime disturbances can propagate is c, the same c that governs electromagnetic waves. When the waves finally reached Earth, 1.3 billion years later, they stretched and compressed spacetime at the location of the LIGO detectors by an amount about 1,000th the diameter of a proton. The detectors, massive interferometers with arms 4 kilometers long, detected this minuscule distortion. The detection was possible only because the detectors were extraordinarily sensitive and because the signal was strong enough after 1.3 billion years of travel. Subsequent detections have confirmed the picture. Gravitational waves from merging black holes and merging neutron stars all travel at the speed of light. The LIGO detection in August 2017 of gravitational waves from two merging neutron stars was accompanied by a gamma-ray burst detected by space-based telescopes about 1.7 seconds. Later, the gravitational waves and the electromagnetic radiation arrived at essentially the same time after a journey of about 130 million light-years. Both travel at c. The tiny difference of 1.7 seconds over 130 million light-years puts a very stringent constraint on how different the speed of gravitational waves can be from the speed of light. The difference is less than about 3 parts in 1,000 million. Gravitational waves and light travel at the same speed. At c. This is a stunning confirmation that the speed of light is not just a property of light. It is a property of spacetime. All disturbances in spacetime, whether electromagnetic or gravitational, propagate at the same speed. The speed built into the geometry. The neutrino is another particle worth considering in the context of the speed of light. Neutrinos are leptons, fundamental particles with no electric charge. They interact only through the weak nuclear force and gravity. They barely interact with anything. Billions of neutrinos from the sun pass through your body every second without stopping. For decades, physicists thought neutrinos might be massless, like the photon, and therefore required to travel at exactly c. In the late 1990s, experiments studying neutrinos produced in the atmosphere by cosmic rays found evidence that neutrinos oscillate between different types. An electron neutrino can transform into a muon neutrino and back again as it travels. This oscillation is only possible if neutrinos have mass. A massless neutrino, traveling at c, has no rest frame and no proper time. It cannot evolve or oscillate. The discovery that neutrinos oscillate proved they have mass. Very small mass, but mass. The Super Kamiokande experiment in Japan published the evidence in 1998. The results were confirmed by multiple experiments. The physicists Takaaki Kajita and Arthur MacDonald shared the Nobel Prize in Physics in 2015 for this discovery. The mass of neutrinos is not known precisely. Current experimental constraints say all 3 types of neutrino have masses below about 0.1 electron volts each. For comparison, the electron mass is about 500,000 electron volts. Neutrinos are at least 5 million times lighter than the electron, but not massless. And because they have mass, they cannot travel at exactly c. They travel extremely close to c. almost indistinguishably close for most practical purposes. But not at sea. The difference is measurable. In February 1987, a massive star in the Large Magellanic Cloud, a small companion galaxy to our Milky Way, collapsed and became the supernova known as SN 1987A. It was the closest supernova observed since 1604. About 3 hours before the optical light from the supernova reached Earth, neutrino detectors in Japan, Ohio, and Russia detected a burst of neutrinos from the same event. About 20 neutrinos in total across multiple detectors. The 3 hours lead time for neutrinos was expected. When a massive star's core collapses, the first thing produced is an enormous burst of neutrinos. The optical light takes time to work its way through the collapsing star. But the timing also allowed physicists to compare the travel speed of the neutrinos to the travel speed of light. Both had traveled about 160,000 light-years from the Large Magellanic Cloud. The neutrinos arrived a few hours before the photons. Consistent with the neutrinos, having tiny masses, traveling at a speed just barely below c, and having been emitted a few hours earlier during the core collapse, before the optical brightening. The data was analyzed to set constraints on neutrino mass. The very small spread in arrival times of the neutrinos from SN 1987A put limits on the mass. If neutrinos had more than a few electron volts of mass, they would have arrived measurably later and more spread out in time than observed. The limits from SN 1987A were roughly consistent with the much tighter constraints from later laboratory experiments. The point is that the distinction between massless and having any mass at all is sharp. A massless particle travels at exactly c. A particle with any mass at all travels below c, even if the mass is a trillionth of an electron volt, even if the difference from c is 1 part in a billion. The distinction is exact. The photon is massless. The neutrino is not. And that difference is visible in the speed at which they travel. The photon's masslessness has other profound consequences. In quantum electrodynamics, the interaction between charged particles is mediated by the exchange of virtual photons. Two electrons repel each other because they exchange virtual photons. The virtual photons carry the electromagnetic force between them. Because the photon is massless, the electromagnetic force has infinite range. Two charged particles on opposite sides of the observable universe would still exert an electromagnetic force on each other, however faint. The force drops off as the inverse square of the distance, but it never reaches exactly zero. This long range of the electromagnetic force follows directly from the photon's masslessness. Compare this to the weak nuclear force. The weak force is mediated by the W and Z bosons. The W and Z bosons are massive, very massive, about 85 to about 100 times the mass of a proton. Because the force carriers have mass, the weak force has a very short range. The range of a force mediated by a particle of mass m is proportional to the reduced Planck constant divided by the particle mass times c. For the W and Z bosons, this works out to a range of about 10 to the power of minus 18 meters. Less than 1,000th the diameter of a proton. The weak force acts only within atomic nuclei, not across atoms, not between atoms in a molecule. Its extreme short range is a direct consequence of the large mass of its carriers, which is a direct consequence of the Higgs field. The photon doesn't interact with the Higgs field. It remains massless. The electromagnetic force has infinite range. Chemistry is possible. Biology is possible. You are possible. The speed of light, through its connection to the photon's masslessness and the gauge symmetry of electromagnetism, is directly connected to the infinite range of the electromagnetic force. A force with a finite range would not bind electrons to atoms at the distances atoms exist. The atom would not be stable. Chemistry would not work. Life would not exist. The specific speed of light is connected to the existence of chemistry through a chain of reasoning that runs through gauge symmetry, photon masslessness, infinite range of the electromagnetic force, stable electron orbitals, chemical bonds, and the existence of complex molecules. If C were different and the photon had mass, the atom would be different. Chemistry would be different. You would not be here. Light speed also connects to nuclear physics through a different pathway. The nuclear reactions that power stars require particles to tunnel through electrostatic barriers. The quantum tunneling probability depends on the velocity of the particles and on the height and width of the barrier. The barrier height is set by the electromagnetic repulsion between the positively charged protons trying to fuse. That repulsion is governed by the fine structure constant, which depends on C. The Sun fuses hydrogen nuclei, protons, into helium nuclei. For this to happen, two protons must approach close enough for the strong nuclear force to take over from the electromagnetic repulsion. The strong nuclear force binds protons and neutrons together in nuclei. It acts only over very short distances, roughly the size of a proton. The electromagnetic force repels the protons at larger distances. For fusion to happen, the protons must approach within the range of the strong force, despite the electromagnetic repulsion. In a star's core, where temperatures reach tens of millions of degrees, protons are moving fast, but not fast enough, classically, to overcome the barrier. Quantum tunneling is required. The proton quantum mechanically tunnels through the barrier it classically could not surmount. The probability of this tunneling depends on the ratio of the electromagnetic repulsion energy to the proton's kinetic energy. The electromagnetic repulsion depends on the fine structure constant, which depends on C. If C were different, the fine structure constant would be different. The height of the electromagnetic barrier would be different. The tunneling probability would be different. The rate of nuclear fusion in stars would be different. Stars would burn at different rates. If the fine structure constant were much larger, the electromagnetic barrier would be higher. Tunneling probability would drop. Stars would fuse hydrogen more slowly. They would be cooler and dimmer, longer lived. If the fine structure constant were much smaller, the barrier would be lower. Fusion would happen too easily. Stars would burn through their hydrogen too fast. No stable stars burning for billions of years. No time for planets to form and for life to develop. The specific value of C contributes to the specific value of the fine structure constant, which contributes to the specific rate of nuclear fusion in stars, which contributes to the age and stability of the universe required for life to emerge. It is all connected. Physicists sometimes talk about the hierarchy problem, and it is worth understanding what it reveals about the speed of light. The Higgs boson was discovered at about 133 times the mass of the proton. This mass is large enough to give the W and Z bosons their observed masses, which are required to make the electroweak theory work as observed. But the Higgs mass is disturbingly small compared to what quantum field theory would naively predict. In quantum field theory, the mass of any particle receives corrections from virtual particles in loops. These loop corrections can be enormous. For the Higgs boson, the natural expectation from quantum field theory is that the mass would be pushed up toward the Planck mass, which is about 10 to the power of 19 times the mass of the proton. The Planck mass is about 122 micrograms. The observed Higgs mass is about 10 to the power of 17 times smaller than the Planck mass. To get a Higgs mass as small as observed, the loop corrections must cancel each other almost perfectly. The cancellation must be accurate to about 30 significant figures. This is called fine-tuning. Physicists are uncomfortable with fine-tuning because it suggests either an enormous coincidence or a hidden symmetry or mechanism that enforces the cancellation. The most popular proposed solution is supersymmetry, which would pair every known particle with a supersymmetric partner. The loop corrections from ordinary particles and their supersymmetric partners would cancel by symmetry, naturally giving a small Higgs mass. Supersymmetry has not been found at the Large Hadron Collider at the masses where theorists expected it. The hierarchy problem remains unsolved. But why does it connect to the speed of light? Because the Higgs mass sets the scale of electroweak symmetry breaking. It sets the masses of the W and Z bosons. The masses of the W and Z bosons, through the electroweak coupling constants, set the fine structure constant. And the fine structure constant, as discussed, depends on C. The whole structure, the electromagnetic constant, the weak coupling constant, the boson masses, the Higgs mass, and the fine-tuning that is required to keep all of this at the observed scales is connected in a web. The speed of light sits in that web, not as a passive observer, as an active participant. Change it, and the web shifts. The hierarchy problem, unsolved as it is, points to deep structure below the standard model, structure that physics has not yet uncovered, structure that might, when found, illuminate why C has the value it does. There is another constant worth knowing about, one that sits alongside C at the foundation of quantum mechanics. Planck's constant, named after the German physicist Max Planck, who introduced it in 1900. Planck was trying to explain the spectrum of light emitted by hot objects, called blackbody radiation. Classical physics predicted that a hot object should emit increasing amounts of energy at shorter and shorter wavelengths, without limit. This was called the ultraviolet catastrophe, because the prediction said a hot object should emit infinite power, which is obviously wrong. Planck found that if energy could only be emitted in discrete chunks, quanta, whose size was proportional to the frequency of the radiation, the catastrophe disappeared. The proportionality constant between the energy of a quantum and its frequency is what we call Planck's constant, symbolized by h. Planck's constant has a value of approximately 6.6 times 10 to the power of minus 34 joules seconds. It sets the scale of quantum effects. The smallest possible action in quantum mechanics is of order h. Heisenberg's uncertainty principle is written in terms of h. The sizes of atoms are set by h. The energy levels of electrons in atoms are set by h. The energies of photons are set by h. A photon of frequency f has energy equal to h times f, and Planck's constant is connected to the speed of light in several ways. The fine structure constant is defined as the square of the electron charge divided by 4 pi times the permittivity of free space times h bar times c, where h bar is h divided by 2 pi. Change c or h, and the fine structure constant changes. The Bohr radius, the characteristic size of the hydrogen atom in its lowest energy state, equals h bar squared times 4 pi times the permittivity of free space divided by the electron mass times the square of the electron charge. The electron mass depends on the Higgs field. The permittivity of free space is connected to c, the Bohr radius, and therefore the size of every atom depends on c through this chain. The speed of light is not just about how fast light moves. It is connected to the size of atoms, to the energy levels of electrons, to the wavelengths of light that atoms absorb and emit, to the chemistry that atomic sizes and energy levels make possible, to the biology that chemistry makes possible. To you, there is a concept in physics called the light cone. It is one of the most elegant geometric ideas in all of science. Imagine a space-time diagram. Time runs upward. Space extends horizontally. You sit at the center of the diagram. Your position in space and your position in time define a point, your here and now. A light cone is the set of all paths that light could travel to and from your here and now. Imagine turning on a flashlight and shining it in all directions simultaneously. The light spreads outward. In the space-time diagram, this appears as an expanding circle getting larger as time increases. In 3 spatial dimensions, it is an expanding sphere. In the space-time diagram, the path traced out by this expanding light sphere is a cone pointing into the future. The walls of this cone represent the paths of photons moving at c in all directions. This is your future light cone. Every event you can potentially affect is inside or on the surface of your future light cone. If an event is outside your future light cone, you cannot influence it. You cannot send any signal, any particle, any influence to it. No cause you generate can affect it. Conversely, your past light cone contains all the events that could potentially have affected you. All events that could have sent any signal, any particle, any influence to your current location are inside or on the surface of your past light cone. Events outside your past light cone could not have caused anything happening to you now. The light cone divides all of space-time into 3 regions. The causal past, the events that could have affected you. The causal future, the events you could affect. And the causally disconnected region, the events that have no causal connection to you at all. This is the geometric structure of causality in space-time, and it is entirely determined by the speed of light. The surface of the light cone, the boundary between what can and cannot have causal connections, is defined by c. Change c, and the light cones change. Change. The light cones and the causal structure of the universe changes. What can influence what? What can be affected by what? The structure of cause and effect. C is the geometric constant that defines causality in space-time. Now, think about what it means that we can measure the speed of light at all. Measurement requires a measuring instrument. The measuring instrument is made of atoms. Atoms are held together by electromagnetic forces. Electromagnetic forces are carried by photons. The photon's properties, including its masslessness and its speed, determine the strength of electromagnetic forces. Electromagnetic forces determine the structure of atoms. The structure of atoms determines the properties of matter, including the matter that measuring instruments are made of. The measuring instrument we use to measure the speed of light is made of atoms whose properties depend on the speed of light. There is a circularity here, a deep one. The speed of light shapes the universe in which we exist. It shapes our atoms, our chemistry, our biology, our brains. It shapes the instruments we use to observe the universe. And therefore, it shapes our ability to observe and measure itself. This is not a paradox. It is a feature. The universe is self-referential. The constants that shape the universe shape the beings within it who measure those constants. There is no outside view, no position from which to observe the universe with instruments not made of that universe's stuff. We are inside what we are measuring. The speed of light is the speed at which the electromagnetic interactions holding our instruments together propagate. It is simultaneously what we are measuring and part of what makes the measurement possible. This self-referential character of physics is part of why the question of why the constants have the values they do is so difficult. We cannot step outside and ask what the universe would look like with different constants from a neutral position. We are inside the constants, made of the constants. Our cognitive apparatus, our brains and sensory systems are products of those constants. Whether we could even understand a universe with different constants is unclear. Our intuitions about physics are shaped by the physics of this universe. The way we reason about cause and effect is shaped by living in a universe where causality is structured by C. The way we experience time is shaped by the time dilation effects that C implies. The chemistry of our neurons, which underlies our ability to think at all, is shaped by the fine structure constant, which depends on C. We are not neutral observers of the constants of nature. We are expressions of them. This does not make the question of why they have the values they do unanswerable, but it adds a layer of difficulty. The answer to why C is what it is would have to be an answer that we, products of that C, can comprehend. The universe's constants may have a logic that is accessible to minds shaped by those constants. Or the constants may be such that the only minds that can exist to ask about them are minds that find them to be exactly what they are. Physics cannot currently distinguish between these possibilities. What it can do is describe the structure with extraordinary precision. And that description itself is one of the remarkable achievements of a species whose existence depends on the very structure it is describing. The history of the speed of light is, at its core, a history of understanding becoming deeper. Romer had a number, a rough measurement of how fast light moved. He did not know what it meant. He did not know it would turn out to be the conversion factor between mass and energy. He did not know it would define the meter. He did not know it was the speed of causality. He did not know it was a property of space-time geometry. He had a number. Maxwell found the number in equations of electricity and magnetism. He still did not know what it meant in terms of space-time. He thought there was a medium, the luminiferous ether, through which light waves propagated, and that c was the speed of waves in that medium. He was wrong about the ether. But his equations were right. Einstein removed the ether, showed that c was constant for all observers, made it a property of space-time rather than a medium. Suddenly, the number meant something far deeper. Heisenberg, Schrödinger, Dirac, revealed the quantum nature of the electromagnetic field. The vacuum, the photon. The number became even more embedded. Higgs, Englert, Brout, and the others explained why the photon was massless, why the number applied to the photon specifically. Each generation added depth. Each step connected the number to something more fundamental. Whether there is a deepest level, a final explanation is unknown. Physicists hope for one. The history of science suggests one may exist. But it has not been found. The number stands. 299,792,458 meters per second, measured first from the moons of Jupiter, now defined as the meter itself, and, at its foundations, still a mystery. In the last 100 years, physicists have built up an understanding of the speed of light that moves through distinct layers, each one deeper than the last. The first layer is experimental. Light moves at approximately 300 million meters per second, measured first roughly by Romer in 1676. From the timing of Jupiter's moons, refined by Bradley in 1728 using stellar aberration, measured in laboratories by Fizeau in 1849, Foucault in 1850, Michelson through multiple decades of work, now defined exactly in our system of units. The second layer is Maxwell's electromagnetism. That speed is not a property of light specifically. It is the speed at which any electromagnetic disturbance propagates through the vacuum. It emerges from the permittivity and permeability of free space. Two constants measured in laboratories using capacitors and coils with no connection to optics. The third layer is Einstein's relativity. That speed is not just a property of electromagnetic waves. It is a property of the geometry of space-time. It is the conversion factor between space and time. It is the speed of causality. All observers in all states of uniform motion measure the same value for c, and space-time bends to ensure this is so. The fourth layer is quantum mechanics and quantum field theory. The vacuum is not empty. It is a quantum medium whose ground state has structure, energy, and physical properties. Those properties determine how fields propagate. The photon is massless because of the gauge symmetry of electromagnetism. Massless particles must travel at exactly c. The fifth layer is the Standard Model. c is embedded throughout the theory. It appears in every relativistic equation, in the energy-momentum relation, in the gauge structure, in the coupling constants, in the masses of particles. It is a free parameter of the Standard Model, measured, not derived. Below the fifth layer? Unknown. This is where the confirmed, tested, experimentally grounded physics reaches its current edge. Below it may be string theory, loop quantum gravity, or something nobody has imagined yet. A framework in which c is derived from something deeper. That framework does not yet exist in a form that makes testable predictions about c. The most honest answer to the question of where light gets its speed from is layered. Layer 1, from the electromagnetic properties of the vacuum, from the permittivity and permeability of free space. These set the speed at which electromagnetic disturbances propagate. Layer 2, from the geometry of spacetime. The speed of light is built into the spacetime metric. It is the maximum speed of any physical influence. It is a geometric property of the universe, not just a property of electromagnetic waves. Layer 3, from the masslessness of the photon. The photon is massless because the gauge symmetry of electromagnetism requires it. massless particles are constrained by special relativity to travel at exactly c and at no other speed. Layer 4. From the structure of the quantum vacuum. The vacuum has a non-zero Higgs field that gives particles their masses. The photon does not couple to the Higgs field. It remains massless. The vacuum has electromagnetic properties, the permittivity and permeability that reflect the ground state of the quantum electromagnetic field. Those properties set C below layer 4. Why does the quantum vacuum have the structure it has? Why do the constants take the values they take? Why does the gauge symmetry of electromagnetism have the particular mathematical form it has? Unknown. Those questions live at the frontier, the place where the equations go quiet and the next generation of physics has not yet arrived. 3.5 centuries of science have carried us from a rough estimate made by watching Jupiter's moons to a number precise enough to define the meter. From a curiosity about whether light had a speed at all, to a recognition that the speed of light is a property of the geometry of the universe. From a single number measured by astronomers to a constant woven through every equation of modern physics. Every layer of understanding added depth. Every layer revealed that C was more fundamental than the previous layer had suggested. And the deepest layer we have reached still does not answer the question at the bottom. Why this speed and not another? Why is the permittivity of free space approximately 8.85 times 10 to the power of minus 12 farads per meter? Why is the fine structure constant approximately 1 over 137 and not 1 over 200? Why does the universe have the quantum vacuum it has? Those questions are open. They may be answered by a future theory. They may turn out not to have answers within physics as we understand it. They may require a kind of physics that does not yet exist. History suggests more layers will be found. Every previous generation of physicists thought they were approaching the bottom. Newton's mechanics seemed complete until Maxwell. Maxwell's electromagnetism seemed complete until Einstein. Classical physics seemed nearly finished until quantum mechanics. The Standard Model seems extraordinarily precise and comprehensive until you ask why its parameters take the values they do. The pattern is consistent. There is always more below. The next time light reaches your eyes, whether from a lamp in your room or from a star that has spent thousands of years in transit, you are receiving an electromagnetic disturbance that traveled through the quantum vacuum at the speed encoded in the fabric of spacetime, the same speed that Maxwell extracted from two constants of electricity, the same speed that Einstein made the cornerstone of spacetime geometry, the same speed that makes the photon massless by virtue of gauge symmetry, the same speed that defines the meter, the same speed that makes chemistry work as it does, and therefore makes your existence possible. Every photon that has struck every human eye in the entire history of the species traveled at the same speed, 299,792,458 meters per second. Not because anyone decided, because the universe is built in such a way that this is the only speed a massless electromagnetic disturbance can travel through this quantum vacuum in this space-time. 3.5 centuries of chasing a number. And the question of why it is that number, rather than something else, is still, at the very bottom, open. Good night.